novel, I think. So just to give an introduction to Tung, so Tung is a second year PhD student in computer science at UCLA and is interested in decision making, sequence modeling, and uncertainty quantification. And Tung has selected sustainability and climate change as an area of focus for his research. And I was just having a chat with Tung here just a moment ago. I know you're very keen to work together and start collaboration. So we've agreed that we'll share Tung's email after the talk, and then people can get in touch. So I'll just let you go ahead. Really looking forward to this. So thanks for being willing to do it at like morning in the West Coast. So
no, it's a good. So hi everyone, my name is Nguyen, and thank you for having me here. Thank you for the invitation, and I'm very happy to present our recent work, ClimaX, a foundation model for weather and climate modeling. So this is actually a joint collaboration with Microsoft. So we have myself, Johannes, Ashish, Zaish, who come from Microsoft, and my PhD advisor, Aditya Grover. So as we already know, like we see on TV and social media and news, weather modeling and climate modeling is becoming increasingly important because we see all these climate change happening, all these extreme weather events happening more frequently, more damaging, and also even more unpredictable. So given this, it's very important that we can we can predict the weather and model the climate reliably and accurately. So right now, the most common approach for modeling the climate and weather is still based on the numerical methods, where we basically encode a lot of differential equations that are based on the laws of physics, fluid motion, and chemistry. So these models have been developed by climate scientists for like so many years, and they know how different climate variables interact, and they encode that knowledge into these differential equations in order to make prediction for the future. And these models, they have been very useful. They can be used for a lot of different tasks. So we can use the same set of differential equations for different tasks. For example, climate projections or weather forecasting. And these models, they are white box. So white box in the sense that because they encode explicitly these equations. So whenever the model makes a prediction, we know why it is making that prediction. So like we can open the box, we can see inside how it is making that prediction. However, these models are also very well known to be slow and computationally expensive. So in order to run these models, we often require supercomputers. And also they don't have an inherent mechanism to automatically improve given more data. So the thing is, these are very explicit models. So we have like these explicit equations that cannot be like automatically updated over time given more data. And an alternative approach to model the weather and climate is data-driven or simply deep learning. So the main idea is actually very simple. We have access to a historical data set, for example, the weather, and then we can train a deep neural network on that data so that we can use the model later on to make future predictions. So in this diagram, you can see that, for example, we can have weather bands, which is like a standard data set for weather forecasting. We have a chaining algorithm. We use the chaining algorithm to train a neural network that can be used to make future prediction for the weather. And these models, they perform significantly fast predictions compared to numerical methods. It can like the prediction can happen in like a few seconds compared to a few days of numerical methods. And recently, we have seen that these models can actually achieve very competitive accuracies compared to the numerical baselines. However, they also have some drawbacks. So because these models, they are trained, they learn from data, completely from data. So they are not exactly explicitly rooted in physics. So what I mean by that is sometimes these deep learning models can make very wild and very wrong predictions, physically wrong or physically impossible predictions. So they're not grounded in physics, and also they lack the generality of numerical methods. So I mean, these models, one model can only perform a particular task. So if, for example, if you train a CNN to perform weather forecasting, then that model can only be used to make weather predictions. It cannot be used to make like climate projections and other and do other tasks. So they are very specific, problem specific. And so I assume that not everyone is familiar with climate and weather data. So here's how we kind of like represent this kind of data so that we can learn a CNN, for example. So actually, climate and weather data we can represent in a very similar way to computer vision. So the input is a tensor of shape v times h times w, in which h and w are basically the spatial resolution of the input. So h and w correspond to like the latitude and longitude of the Earth. And then we have v, which is the number of input climate variables. So these variables can be like weather variables like geopotential, temperature, the wind speed, humidity, and other things. They can also be like forcing factors such as CO2 levels, SO2, and other factors. So that's how we represent the input. And we from this input we want to make a prediction on output of a similar shape. So v prime times h prime times w prime. So again, h prime and w prime correspond to like the spatial resolution of the outputs, and v prime is the number of output variables. So the number of output variables can be different from the number of input variables. So for example, we want to make prediction for the temperature, but we condition on, or the input can include other variables like geopotential, humidity, but the output variable can only be temperature. So the number of input variables and output variables can vary depending on applications. So yeah, and feel free to ask me any questions during the talk. Yeah. So that's how we represent climate and weather data in deep learning to train deep learning models. And here are some very recent works, recent advances in the field. So we have three models. We have ForecastNet, Pangu Weather, and GraphCast. And these models are actually very new because they were all invented in 2022. So they have different architectures. They train different architectures, different neural networks. However, if we look from the perspective of weather and climate modeling, they are all doing a very similar thing. So they train on the exact same data set and they perform the exact same task, which is weather forecasting. So again, these models, even though they are very like powerful, very accurate, they are lacking the generality of climate of numerical methods where one model can perform multiple tasks. And if we look at the field of like natural language processing and computer vision, this is actually very similar to how people train their neural networks a few years ago. So whenever you want to perform a specific task, for example, question answering, sentiment analysis, or object recognition, you first collect the data for that particular task, and you train a neural network that can be used to make prediction for that particular task only. So we call this task-specific models. However, there has been a significant paradigm shift from training task-specific models into training foundation model. So the idea is actually very simple. So first, you collect a huge data set. So the data set can span so many different tasks. You train a deep neural network, which we call a foundation model. So a foundation model is nothing but a very huge neural network. And then after pre-training, we can adapt to multiple downstream tasks by two ways. We can either fine-tune the model on the task-specific data, or we can even perform zero-shot learning where there's no fine-tuning happening. So this is a new paradigm where we can pre-train a huge network that can be generally useful for a lot of different downstream tasks. And this has been very successful in vision and language. And people found out that these foundation models, they can generalize very well to tasks that are even unseen during training, that are actually very different from pre-training. So that is a very good thing. And one more advantage of these foundation models is that because it has been trained on a lot of data, in some sense, it captures the general structure of the data. And after pre-training, we only require very little data to fine-tune the model on a particular task. So that's a good thing, because in climate and weather, we know that not every task has like a lot of data to train deep neural networks. So that's a very good direction to go, I think. Yeah, so ClimaX is actually inspired a lot by these works in climate, in language and vision, and that's why we want to demonstrate the first foundation model for weather and climate. So ClimaX can be pre-trained on different heterogeneous data sources. So given these data sources, ClimaX can be pre-trained on all of them. And then after pre-training, ClimaX can be fine-tuned to perform a wide range of different tasks in both weather and climate regimes. So here's just a summary of what ClimaX can do. So ClimaX can make weather forecasting with different timescales from nowcasting, which is a few hours ahead, until like a few months ahead. And it can make predictions for regional and global data. And also it can make climate predictions, for example, like climate projections and climate downscaling. So ClimaX can actually be applied to so many different downstream tasks after pre-training. Yeah, so in order to like design ClimaX, we need to define three components. So because when we look at how people do it in computer vision and in language, there's actually a very standard recipe for training foundation models. So we basically pre-trained a deep architecture on a large dataset using an unsupervised objective. So the architectures can be transformers, it can be CNN or VIT. The dataset can be the text corpuses that we collect from the internet. It can be millions of natural images if we want to pre-train a foundation model for vision. And the objective function can be next token prediction, which is commonly used in language modeling. For example, in GPT models, that is the objective that people use to train GPT. And in vision, it can be mass image modeling or contrastive learning. So this is a very common recipe for language and vision. And basically what we need to do is we need to design these three components for ClimaX. So is there any question until now?
No, it's to me very clear anyway. I don't know if there's anyone in the room.
Right. Yeah. So the first thing is the pre-training data. So how do we get a huge data set to pre-train ClimaX? And we came up with the idea of using simulated data. So simulated data is basically the outputs of different climate models. So the outputs of different numerical methods. And we use the CMF6 data collection, which is a huge data collection because we have access to more than 100 numerical methods. That means we have access to more than 100 data sets to pre-train the model. And each data set can contain a different set of climate variables. And the reason we choose simulated data over like observational data or satellite data is simply because we can, in theory, have infinite simulated data because whenever we want to have more data, we just use these numerical methods to make prediction for the future, and that's why we can have more data. And I can say it is like free data because we don't have to collect manually in any sense. We only have to run these models, forward these models in time to collect their outputs, and then pre-train ClimaX on their outputs basically. So that's why we decided to use CMAP6 simulated data collection. And in terms of the architecture, in the first place, we decided to build ClimaX upon VIT. So VIT is a very common architecture in vision. So the main reason why we chose VIT over other architectures like CNN and graph neural networks is because it's flexibility and scalability. So flexibility in the sense of like VIT can be applied to so many different settings. So it can be pre-trained on one resolution and then fine-tuned on a different resolution. It can be pre-trained on global or local data and then fine-tuned on either global or local data. So it is very flexible in how we want to use it. And it is also very, very scalable. So what I mean by scalable, whenever we increase the number of parameters and increase the number of training data, the amount of training data, we see that the performance of these VIT models increases significantly with respect to data size and model size. And that is also what we want to achieve with ClimaX, because we know we have access to a lot of data and we can train big models. So that's why we went with VIT in the first place. So for anyone that is not familiar with VIT, this is like a very quick introduction into how VIT works. So the input, you can think of the input as an image. You will tokenize the image into smaller tokens. And each token contains all the input variables. So if you have 3 channels or 3 variables in the input, each token will contain all these 3 variables. So now we transform the original image or the original input into a sequence of tokens. And then we basically feed this sequence of tokens into the transformer's backbone. And then we have a prediction head on top of the backbone to make prediction for the future. So this is just a very quick introduction into how VIT works with like image-like data. However, as you can also recognize in this picture, if we want to train the model on different data sources, and each data source can contain a different number of variables, then VIT cannot be applied. So the main reason is because of the tokenization module in VIT. So as you can see in the figure, each token in VIT actually contains all the input variables. And if we have like different input variables for each of the data sources in the training data, then this cannot be applied because the tokenization scheme will not work for different data sources. Is this clear for everybody?
I have a question about the architecture here, if that's okay.
Yeah. Yeah.
So in this diagram, it sort of looks like that you're trying to predict the entire 2D field in the output here out of this prediction head. How does it work? Because then the architecture doesn't know where these tokens are sampled from in space, right?
Well,
how does
the model is actually aware of what the tokens come from. So for example, you have an input of for example 32 times 64, and each token is like 2 by 2. Then basically you flatten the image into a sequence of tokens, and then the transformer backbone will keep the same length of the sequence. And then given the output sequence, we can have a prediction head on top of the output sequence to make a prediction that gets back into the image space, basically.
Okay, so you turn it into this 1D sequence, and then in the prediction head, that 1D sequence becomes a 2D image again.
Yeah. So the idea is actually, so the big idea is we first transform the image into a sequence, 1D sequence. The transformer backbone will transform this sequence further, like process this sequence further, and then on top of the final sequence, we can have a prediction head that basically transforms back the 1D sequence into an image.
Okay, cool. And then the sort of attention within the transformer is the bit that decides which part of the input sequence is important for making different parts of the output.
Yeah, exactly. Yes.
Yeah. Okay. Very cool. Okay.
Yeah. Yeah. So similarly to like how we use like transformers for language, for natural language processing, the only difference between VIT and transformers in language is that we have this tokenization scheme where we have to first tokenize the input into a sequence. Yeah, and given the sequence, everything remains very similarly to how people do it in language.
I assume that the size of this token somehow becomes important to the.
It is important because if we like use a too large token, and then maybe we are missing some very important information in the input.
Mm-hmm. And they're never overlapping, these tokens, right? They're like discrete.
Yeah, they are not overlapping.
Yeah. Okay.
Yeah.
Cool. I could ask loads more questions, but I'll save them for the end. I think there's one from the room.
Yeah. So as you can see, because of the tokenization scheme, this kind of architecture will not work with different data sources because of the problem that I talked about. Because of the tokenization scheme, always assumes that the number of input variables is fixed, but it is not fixed in climate and weather because each dataset has a different set of climate variables. So this is like perfectly fine for vision, for image data, because for image we always have RGB channels, so always the exact same 3 channels in the input. However, it is not the case in climate and weather. So that is why we need a different tokenization scheme. So the idea is that now instead of like tokenizing the entire input into one sequence, we will tokenize each climate variable separately. So for example, if we have 3 input variables, which are the humidity, wind, and the temperature, we can tokenize them into a sequence separately. So we have a sequence for humidity, we have a sequence for wind, and we have a sequence for temperature. And then we simply concatenate all the subsequences into a very long sequence that contains all the subsequences corresponding to different climate variables. So by doing this, the model can deal with different number of input variables because we are tokenizing them separately. However, there's a huge problem with this tokenization scheme. So because now we are tokenizing each variable separately and then combining all the subsequences into a single sequence. The single sequence can be super long because we are concatenating like a lot of different climate variables. And in our application, the number of input variables can be like 50. So this is too expensive to run any deep learning model, and also especially for VIT, for transformer, because the computational memory complexity of transformer is quadratic with respect to the sequence length. So if we increase the sequence length by 50, then the complexity will increase by more than 2,000 times. So that is excessively computationally expensive because of the long sequences. So we have to somehow process this very long sequence before feeding into the VIT backbone. And we propose an aggregation scheme to summarize all these input variables into one single vector. So the idea is that for each spatial location in the input map, we will have a cross-attention operation which simply summarizes all the input variables into one single vector. So now instead of having V tokens, we only have one token. And we can do that exactly the same for each spatial location in the input. So we do this for the first token, for the first spatial location, we do it for the second spatial location, and we do it for every other spatial location. And by doing this, we have actually reduced the sequence length by V times, which is a lot of saving in computational complexity. Yeah. So so this is variable aggregation scheme, which is an important contribution of our work in order to process different data sources with different number of variables. And here is how the entire architecture looks like. So we have an input that can contain different number of input variables. We tokenize each variable separately and then concatenate all the variables into a long sequence. After that, we use an aggregation scheme to summarize V input variables into one single vector for each spatial location. And then after that, we feed the preprocessed sequence into the VAT backbone and then prediction head to predict the future. Okay, this is the final slide of the architecture. So I'm happy to answer any questions if there's any.
Can you hear me?
Yes, you might want to move a little forward because the microphone isn't picking it up very well from the back.
Now better?
Yes, better now.
Yeah, I was going to ask, so in the positional encoding of the tokens, do you include some information about the variable type? So I guess the special information is encoded in the positional encoding, but
yeah, that's actually a very interesting question. So we actually did that. So as you can see on this slide, there are so many tokens. If we simply feed this entire sequence into VAT backbone without informing where the token is coming from, then the model will have a difficulty learning from this sequence. So we do add positional embedding to let the model know what spatial location each token is coming from, and also we have variable embedding to let the model know what variable each token belongs to. So we have two kinds of positional embedding, one for the variable and one for the spatial location.
And you just aggregate both into a single one?
Yes, I just add them both to the tokens.
Okay.
I have another sort of related question, which is when you cut this big image up into these smaller tiles that you tokenize, what do you actually use to create the embedding vector for those pixel values? Do you just flatten the 2D array, or do you have some convolutional method or something to extract the?
So the encoding can be a CNN or can be just a linear layer. We can flatten and use a linear layer, or we can use a CNN. And in this work, I use a CNN specifically, but only for the very first step of tokenizing the input into a sequence of tokens.
Yeah. Okay. Thanks.
Yeah. All right. So this is the architecture. And after designing the architecture, we need to design the positioning objective. So our intuition when designing the objective is that after positioning, we want to have a generally useful model that can be fine-tuned on different tasks. So to be useful for different tasks, what we think was the model had to capture the spatial and temporal aspects of climate data, because we know that climate data, weather data, is all involving in time and space. So the model had to somehow capture those aspects in order to generalize well to downstream tasks. So that's why we decided to use a future prediction objective. So the idea is that given the current condition of the weather, we pre-train the model to predict at a arbitrary time in the future the condition of the weather. So what I mean by arbitrary time in the future is that during pre-training, we actually randomize the lead time that the model is making predictions at. So we randomize lead time from 6 hours to 1 week. So during pre-training, the model can make predictions of the weather at 6 hours ahead or up until like 1 week ahead. And in this formulation, you can see that so the first term is the prediction of the model, and the second term is the ground truth. And you can see the delta t here is the lead time, like how far in the future the model is making prediction at. And the delta t is actually randomized during pre-training, so it is only it is not a fixed value, but it actually changes during pre-training. And this is the overall like pre-training procedure of ClimaX. This can be like a bit too complicated, so I think I can go like one step at a time. So first, the model will receive an input of shape v times h times w. So we have different climate variables. Then we sample the lead time from 6 hours to 1 week, and then we get the corresponding ground truth at that particular lead time. So now we have both the input and the ground truth, and we are ready to train the model. And the first step in training the model is we have to tokenize these input variables separately. And then after the tokenization, we apply the variable aggregation scheme to kind of like summarize these tokens to make a shorter sequence for the model to learn. After that, we add the lead time embeddings, variable embeddings, and positional embedding before feeding this sequence into the VAT backbone. So this is a very standard technique in how people use VAT. We have to add all these embeddings to let the model know the difference between different tokens. Oh, sorry. What did I do? Oh, sorry. Somehow I came to the last slide. Yeah, so we feed the sequence into the VAT backbone. We have a prediction head, and we predict the output. And now we have the prediction. We have the raw truth. We basically compute the loss function and update the model. So this is the entire pre-training procedure of ClimaX. And I think this figure is actually important. So I'm very happy to answer any questions, if any. Okay, so if that's, yeah.
No, I was just saying none from me. It's very clear. So keep going.
Thank you. So I think we can continue. Yeah, so this is pre-training, and after pre-training, we want to actually use ClimaX for different downstream tasks. So I can present two sets of tasks that we actually applied ClimaX on. So we have weather tasks and climate tasks. So in weather tasks, we can make either global prediction of the entire weather of the entire globe, or we can like make regional prediction for on specific region, for example, the North America. And we can also consider making predictions for like long lead times, for example, like a few weeks ahead or even a few months ahead. And we can use ClimaX to perform climate projections or climate downscaling. So the first task we consider is global forecasting. So the task here is we want to forecast the future weather on the entire globe, given the current global weather condition. So this is the fine-tuning protocol, which is, you may see that this is actually very similar to the previous figure. So the only difference here is that doing fine-tuning, we fix the lead time. So for example, if we want to predict 3 hours or 3 days ahead, then we fix the lead time to correspond to that particular lead time. So what I mean by that is that we fine tune the model to make weather forecasting, to make weather prediction at a particular lead time during fine tuning. We do not randomize the lead time. And this is the quantitative result. So we compare ClimaX with IFS, which I think is the current gold standard in weather forecasting. So IFS is a numerical method, and ClimaX is a data-driven method or a deep learning model. And as you can see on this slide, we measure two metrics, RMSE and ACC. So lower RMSE is better and higher ACC is better. So as you can see, if we make predictions from like 1 day, 3 days to 7 days ahead, I think IFS is still somewhat doing a better job than ClimaX. However, if we make predictions at longer lead times, like 2 weeks or even 1 month, then ClimaX actually outperforms the IFS baseline, and this is a very encouraging result, I can say, because IFS was like designed by climate scientists that encode a lot of knowledge about the weather, about the climate, about the atmosphere, and it has been like continuously updated and improved over so many years. And ClimaX, by pretraining and fine tuning on weather data, it can actually match or even outperform IFS at some lead times. And here are some qualitative results. So on the first column of the figure, you can see the initial condition, which is the input of the model. The second column is the ground truth, the data ground truth. The third column is the prediction of the model. And the last column is the bias, which is basically the difference between the ground truth and the prediction. And as you can see, if we make predictions from 6 hours to like 5 and 7 days, the model actually performs very well. It captures well the underlying structure of different climate variables. So in this slide, I'm showing temperature and wind speeds. However, if we increase the lead times to say 2 weeks and 1 month, the model kind of like makes a very blurry prediction. So we hypothesize that just because the weather is impossible to make an accurate prediction, if we want to make a very long time scale prediction, because the weather system becomes kind of like chaotic after a certain lead time. So that is why the model is doing not a very good job at making predictions at 2 weeks and 1 month. And I think a better way to perform weather forecasting at those very long lead times is we have to use like an ensemble of models. So we train, let's say 50 models and then combine them together to make predictions for longer lead times from 2 weeks until 1 month. I think that's also one common practice that people have in weather forecasting. Whenever we want to make predictions at a very long lead time, we often have to use the ensemble of different models. Yeah, so this is global forecasting. And the second task that we consider was regional forecasting. So previously we predicted the weather for the entire globe, but now we want to make prediction for one specific region, because the reason is we do not always have access to like global data, and each research group, they may want to use ClimaX to make prediction for a particular region of the Earth. For example, if I care about making predictions for North America, then I can take ClimaX and make prediction for North America only. So this diagram shows how we can apply ClimaX for regional forecasting. So the only difference between this and global forecasting is that now the input is only one local region of the entire globe. So we only feed the tokens that correspond to these regions to the model. Instead of feeding all the tokens that belong to the entire globe, we now only feed a subset of tokens to the model that belong to that specific region, and the model can make corresponding prediction for that prediction for that region. And here's the quantitative comparison. So we compare ClimaX with different baselines because this benchmark was not considered in previous work. So we compare ClimaX with some of the baselines that we can think of. We compare ClimaX with ResNet and UNet. ResNet and UNet are trained on the local data and tested on the local data. ClimaX was pre-trained on global data and fine-tuned on local data. And interestingly, we also consider two baselines. And the first baseline is the CliVIT model. So CliVIT is basically a model that there's no pre-training. So CliVIT is basically ClimaX without pre-training. And we also have one more baseline, which is ClimaX positional embedding interpolation. So that's a very long name, but the meaning of that is we can actually pre-train ClimaX on data with a smaller resolution, and then after pre-training, we can fine-tune the model on a higher resolution data. And the way we do it is we interpolate the positional embedding, which is a very standard technique that people use in VIT models. So we include that baseline to show that ClimaX is actually very flexible in how we want to use it. So we can pre-train on global data, and then fine-tune on local data. We can pre-train on low resolution data and then fine-tune on higher resolution data. So it is very flexible in how we want to use it for our applications. So as you can see on this figure, on this graph, ClimaX is still the best performing method, and following ClimaX is the ClimaX positional interpolation model. So that is very interesting because even though ClimaX positional interpolation was pre-trained on low resolution data, it can generalize well to higher resolution data and outperforms other baselines like ResNet and UNet. Yeah, so the takeaway from this slide is ClimaX can gain strong performance on tasks that have different spatial coverage, so global versus local, and even different spatial resolution from pre-training. And after that, we also consider different tasks from weather forecasting. So we consider climate projection, and the task in this climate projection is we want to predict the annually average statistics of different target variables given the forcing factors. So the task is basically saying that now we know, let's say we know the CO2 level, we know the SO2 level, and we know all the levels of other forcing factors. How do we predict the average temperature, for example, of 50 years from now, for example, given that we have the exact number of the CO2 level. And we use the data set and the evaluation metrics from Climate Bench. And because this is like completely different from weather forecasting. So in weather forecasting, we make predictions temporally. So we make temporal prediction because given the past and the present, we want to make predictions for the future. However, this is somewhat different because we are making predictions given the forcing factors, meaning that we want to predict how the weather system responds to different conditions of the CO2 levels, basically. So this is not a temporal forecasting task, and that means this downstream task is actually completely different from pre-training, both in terms of the nature of the task and the number of input and output variables that we are trying to predict. And this is how ClimaX performs. So again, we compare ClimaX with CliVIT, which is a non-pretraining model. So ClimaX without pretraining. We also compare with ClimaX frozen. So ClimaX frozen is an interesting baseline where after pretraining we freeze. So we stop training the VIT background. We only train the encoding part of the model and the prediction head. So we freeze all the attention layers, which is the main computational part of the model. And we also compare with the baselines in the climate bench paper. And among different target variables, among different metrics, ClimaX performs very competitively with the climate bench paper baselines, and even outperform in some climate variables. And even more interesting, the ClimaX frozen model actually outperforms ClimaX. So what that means is that in downstream tasks where we only have access to a very small data set, it is good to freeze the attention layers because that will avoid overfitting issues. And this is true for climate bench because in climate bench we only have like 800 data points, which is very small compared to the size of the model. So in these scenarios, it is very important that we can freeze the attention layers and only train a small part of the network in order to get a better performance. And finally, the final task that we consider in the work is climate downscaling. So the task of climate downscaling is that given a low and bias, low resolution and bias input of the weather, we want to upsample the low resolution input into a high resolution output, and also remove the bias that is present in the input. So in this task, the input and output variables are very similar to pretraining. So we have access to like weather climate variables like geopotential, weather, temperature, and humidity. However, the task nature is actually different from pretraining because again, it is not a temporal forecasting task. So we just want to see if the model can generalize well to this task. And again, we compare ClimaX with ResNet and UNet and the non-pretraining version of ClimaX. And you can see in this table, ClimaX outperforms all the baselines and in all different climate variables. And this shows that even though the model was pre-trained to perform forecasting, which is a temporal task, it has successfully captured the spatial structure of the data, which is important in tasks like downscaling, because in downscaling we want to upsample the input into a higher resolution version. So it is important that we can capture the spatial structure of the data in order to upsample the input. And this is just some visualization of the model. We have the low resolution and bias input. We have the raw truth, which is higher resolution, and we have the prediction of the model. And as you can see, the model kind of successfully upsamples the input. It is missing some fine details of the input of the raw truth. However, it is capturing successfully the general structure of the data of the output. Yeah. And after all those experiments, we also like perform some kind of like analysis to see what makes ClimaX perform very well. So we see how ClimaX scales with respect to data size and model size, because previously we have seen that in language and vision, transformers models scale very well if we increase the number of data points and the model size. So here's the figure that shows the very well scalability of ClimaX with respect to model size and data size. So in this figure, we have 4 different models that correspond to 4 different model sizes. And the biggest model is the ClimaX D equals 2024. And this number is like the dimension of the model, the hidden dimension of the VIT. And on the x-axis of the figure is the data points, the number of data points, and on the y-axis is the error of the model. And as you can see, as we increase the model size and increase the number of training data, the amount of training data, the model becomes more and more accurate. So this shows the model scales very well with respect to data size and model size. And it is actually a very good news because we know if we keep increasing the model size given more computation resources, and if we keep increasing the data size given having access to more data sources, then we can increase the model very easily, increase the performance of the model very easily. And the second dimension, or the third dimension of scaling with ClimaX is scaling with respect to data resolution. So we show that if we increase the resolution that we train the model on, the performance actually increases significantly and consistently for different climate variables. So here I'm showing ClimaX that was pre-trained and fine-tuned on low resolution, and another version of ClimaX that was pre-trained and fine-tuned on a higher resolution of the data. And as you can see, if we increase the resolution, the performance in terms of both the RMSE metric and the ACC metric increases significantly for all the target variables. And this is very consistent across different target variables and across different lead times. So it is again a very good news because we haven't been able to like pre-train and fine-tune ClimaX on the highest resolution data because we didn't have like enough computational resources to do that. But it is good to know that if we have able to more computing resources, we can improve the performance by simply training on a higher resolution dataset. And this is the conclusion of the talk. So we introduced ClimaX, which is to the best of our knowledge, the first foundation model for weather and climate. ClimaX can be pre-trained on diverse heterogeneous data sources that span different climate variables. Thanks to the very flexible architecture, ClimaX can be pre-trained from data with different spatio-temporal coverage and even with different physical groundings. ClimaX can be fine-tuned to solve a wide range of weather and climate tasks in various settings, and ClimaX scales very well with respect to data size, model capacity, and data resolution. And I think beyond ClimaX, there are a lot of interesting directions that we can take. So the obvious one is that we can simply scale up ClimaX. So we can simply increase the model size, we can increase the data size, and increase the data resolution. We can evaluate ClimaX on more tasks, for example, making probabilistic forecasting for longer horizons, or we can make predictions for like extreme weather events. We can also improve the ClimaX in terms of architecture and objective functions, so we can have more sophisticated aggregation schemes. So in this work, we only use like a very simple one-layer cross-tension layer to perform the aggregation that I talked about. So we can have something more complicated and maybe performing better. We can have a more efficient transformer architectures rather than VIT. And we can also think of better pre-training objective rather than future prediction. And even more interesting, we can think about ClimaX similar to GPT-2 in natural language processing, because after pre-training, we have to fine-tune the model to adapt the model to different downstream tasks. However, what we can also do is like thinking about how we can make ClimaX something similar to GPT-3, where we don't even need to do any fine tuning. So after pre-training, we can just let the model look at some of the data points that come from the downstream tasks, and there's no gradient ascent update. There's no optimization doing fine tuning. The model can adapt very effectively to different downstream tasks. Yeah, and that concludes my talk. And if you want to see more details of the paper or the other experiments or the other details and analysis, we have the paper published on arXiv. We have the source code published. We have a website, and also if you want to even check out more the research that we are working on, you can also check out our lab's website that I link here. And I'm very happy to answer any questions via email or via Twitter. So thank you everyone for listening, and yeah, so now I'm happy to answer any questions.
Well, I have loads of questions, but I feel like we should start in the room. Naomi, do you want to organize people?
I have even 2 questions. Hi.
Yep.
One thing I want to clarify: do you, as your input data, do you use one time step, I would call it, or do you use a sequence of time steps?
Yeah, that's interesting question. So in this book, we only consider one time step in the input. So basically what it means is we condition on the weather today to make prediction for the weather in the future. However, it should be beneficial if we consider more time steps. Let's say instead of only using today's weather, we can condition on the yesterday's weather and even longer before that. And my intuition is that if we use more time steps, we should be able to achieve better performance. But in this work, we only stick with using only one time step.
Okay. For the training data, you have said you used climate model predictions, and the climate models currently existing are known to struggle with some processes, like mostly in tropics, some convection, for example. Did you see that affecting the model in some way, and maybe had to like compensate for that?
I see. So I'm not sure about that, because like the model is pre-trained and fine-tuned like completely from data. So everything the model learns comes from the data itself. So I'm not sure if that's a problem. But yeah, as I introduced, as I talked about earlier, all these like deep learning models, they have a drawback of lacking the physics grounding. So they're not implicitly physically grounded. So sometimes they can make very wrong predictions. But that is like an orthogonal direction, I can say, apart from ClimaX.
Okay. And my last question is, in the weather forecasting example, there is this flattening of the RMSE curve, and I'm wondering where that comes from. So when when the blue line like detaches from the IFS score, it basically goes flat. Why is that?
Yeah, so that's again very interesting question. So if you look at the like visualization of the model, you can see that at 7 days and 2 weeks, the model is actually like producing a very blurry output. So I think because of that reason, that is why the model kind of like achieve a very similar RMSE for 2 weeks and 1 month, because basically the model doesn't really make a very good prediction, but only tries to guess as much as possible the output, because the task at making prediction 2 weeks and 1 month ahead is just like too difficult for the model. So it is just trying its best to guess the output. So that's why you can see a flat line if we increase the lead times from 2 weeks to 1 month, because basically the model is just making a very blurry prediction in order to get a very messy number.
Okay.
Another question.
Yeah.
Got another question in the room.
Live for you. I was gonna say, how much time did it take to pre-train the backbone, and how much resources did you use?
Yeah. So to pre-train the backbone, to pre-train ClimaX, I think it took like 1 or 2 days on the low resolution data. And if we want to pre-train and fine-tune, if we want to pre-train the model on the high resolution data, and I think it took like 5 or 6 days of pre-training. Like, yeah, so around those numbers. And how many resources we use? I think for the biggest experiment, I think we used like 5 clusters of 8 V100 GPUs. So there were 40 GPUs in total. Yeah, 40 GPUs in total.
Okay. And another question with what Jacob was saying. So in the downstream tasks, none of them used real-world data. It was all tested on simulated data, or?
Oh yeah, sorry, I forgot to talk about that. Actually, all the downstream tasks used real-world data.
Okay.
So for global forecasting, we use EI5, which is like a reanalysis data set that combines both observational data and like outputs of numerical methods to make like the best estimate of the weather at any point in time. So people often consider EI5 a raw truth of the weather at any point in time. So that is actually a real data set. And also for climate tasks, we use climate bench. So I don't think we can say climate bench is a real data set, because it is not a data set that people actually collect in real world scenarios. But these data sets are like generated from climate models, and that's everything we can do, because like to make predictions 50 years from now, we don't have any real world data. Yeah, but for the global forecasting task, we use real world data. Yeah.
I have a question, if that's okay. I was wondering whether you had looked at the attention map once you've trained into these networks.
Yeah, we actually haven't done that. So because like when working on this project, we were like running against a deadline, so
yeah.
didn't have much time to do all this interesting analysis. But
Yeah.
I think like looking at the attention map is actually very interesting to see how the model looks at different components of the input in order to make a prediction for one particular target variable. My hypothesis is like maybe in order to make predictions for temperature versus making predictions for geopotential, the model may need to look at like different parts of the input. So yes, that's my like intuition.
Yeah, because I mean, of course, so you could use it both as a means to verify that ClimaX is doing what we physically know is meant to happen, right? Because we know, how weather systems move and what trigger things, and there's all these teleconnections around the world that have been studied for decades now. But then the other thing you could do is you could use ClimaX as a means to try and discover things that we don't yet know about in cases where it's making good predictions. In continuation of that, I wonder whether you'd looked at the effect of the size of your tokenization, because it works, of course, quite well here now at this resolution you're at now. But if you wanted to do regional weather forecasting down to, say, kilometer resolution, then probably the token is too big, right?
That is true. So that is one limitation of the work right now, because we were only able to train the model on actually, I think, very low resolution. So I think like 100 kilometers. is like the highest resolution that we train the model on, and to make the model like more practical, more useful, to be actually deployed in real world systems. It is important that we need to use like even higher resolution data and even smaller tokens.
Yeah.
Yeah.
But I think it might not be a limitation though with what the architecture, like the conceptual idea, because with the weather phenomena, we also have idea of a sort of scale separation. Different weather phenomena have different sizes, and also that's why we have global models and regional models and LES models when you get down to the finer scale. And I was wondering whether one could envision a sort of a hierarchy here in a where you don't just tokenize at one resolution or one size, but you tokenize at multiple. I mean that you could possibly, but then the sequence length becomes very long, right? If you go very big.
Like the main bottleneck right now. I mean we can always change the model on high resolution, and we can always decrease the size of the token. But the thing is, like, if we do that, then the sequence will be just too long, and it will just be too expensive. That is why in the end of the talk I talked about why it is important we should use a more efficient transformer architecture, because right now we are just using the vanilla version of transformer. So the complexity of the transformer is quadratic with respect to the sequence length, and maybe we can use like other architectures that are more computationally efficient, that scale better with the sequence length.
Cool. I had just one last question. That's on higher resolution things, but I was wondering whether you considered using this architecture for nowcasting, because that's a situation where we have high resolution radar precipitation measurements at high temporal resolution, but we don't have a sort of a general way of ingesting those into weather forecast models and running them fast enough that we can make a useful prediction. And it feels like, to me at least, that might just be another feature one could just simply add, right? An input field one can add to this. Have you considered doing that?
Yeah, I mean, like, there are a lot of applications we are considering right now. So I think the main problem is like, because we are not aware of those interesting problems, for example, in nowcasting that you just talked about, because we are all like machine learning and computer science backgrounds.
Right.
So we are still exploring different applications that we can apply ClimaX to. And if nowcasting is an important problem, and if ClimaX is applicable, then I think it is interesting to see how ClimaX perform in those scenarios.
Cool. Okay. Well, I'm sure there are people who find that interesting, so we should talk about that later. But yeah, I just want to say, really great talk. Thank you for making it so clear. So I don't know if there's any other questions in the room.
No, I think we're all good.
Okay, well, if we've got no more questions, I think we should wrap up. We've already gone a little bit over time. So thank you again, Tung. That was, I think, really interesting. And I would encourage anyone to get in touch if they have further questions. And I'm sure we'll be talking about ClimaX later in the community's Tung as well, about how we could use it, for sure. So thanks again, and have a great weekend, everyone. Thanks for joining.
Yeah, thank you, everyone. Bye, everyone.
Bye-bye.